Until now, all we've talked about is the 2D coordinate system. And in this chapter, we'll be getting into talking about three-dimensional coordinate system by adding the extra plane with the z-axis as shown here. So if we look over here, we see a 3D coordinate plane. And until now, the 2D coordinate plane really only consisted of the x and the y. So this blue plane we see here should be the familiar coordinate plane we have, the 2D coordinate plane. And now basically what we've added is an extra dimension, the dimension of depth, with this z-axis we have here. So let's start by defining a couple of the terms that we'll talk about. So the directed distance from the xy plane. So this is just a really fancy way to talk about x, y, and z. So the directed distance is really just how far you're going from the plane we're talking about. And the xy plane is the plane that consists of x and y. So the blue plane that we see here in this picture would be the xy plane. And the directed distance would be how far we're moving away from it. So if we go up in this direction we have here, we're basically moving on the z-axis. So the directed distance from the xy plane ends up being z because it's how far we're going from the xy plane. If we're going 1 unit forward up from the xy plane, that would be the z value would be 1. If we're moving 1 unit down, that would be -1. Now the same way we can see the direct distance from the xz plane. If we have x and z, that's going to be this green plane that we have here. And any direction we go from there would be moving along the y-axis. So that would be y. And then finally, as you could probably guess, the directed distance from the yz plane, which is the red plane that we have in this picture here, that would be just moving along the x-axis. So that's just x. So this is just really a fancy way of saying what x, y, and z are. And we can even take this to the two-dimensional world where we have x and y. And if we wanted to formally define x, that would just be how far we're moving from the y-axis. When we move 1 unit to the right of the y-axis, or the positive side of the y-axis, the x value is 1. Now, this is where we'll start to, actually before we start graphing the coordinate we have here, let's talk about the octant system. So octants are basically like quadrants that we have in the two-dimensional world, but in the three-dimensional world we have these things called octants, which is basically 8 kind of sections we can divide the three-dimensional coordinate system into. And I really like this picture we have here because we can really kind of visualize the depth perception of the three-dimensional coordinate plane. And basically what we have here is this right-hand orientation system where when x, y, and z are positive, that's going to be octant 1, and we basically move in a right-hand direction. So basically we'll be moving kind of counterclockwise here. So this is octant 1, where x, y, and z are both positive, or all of them are positive. This would be octant 2. Actually, let me use a different color here. It's kind of hard to see. We'll use black. This is octant 1, octant 2, 3, and 4. We move in this counterclockwise direction. So that's going to be the 4 octants, kind of like quadrants we had. But then now we have another 4, which is where z is going to be negative. So it's basically below the xy plane. So this would be 5, 6, 7 is under the octant 3, so it's going to be over here somewhere. And then finally 8 is under octant 4. So we have this right-hand system. If you want to take your hand out, put your fingers kind of to the right, and that's basically, if you keep going that direction, it's kind of a counterclockwise direction, however you want to think about it. So that's what we call the octants. Basically like quadrants on the 2D, but for kind of modified for the 3D system. So now let's get into graphing these coordinates and stating the octant. So we have a 3D kind of coordinate plane right here. If you can't really see the 3D yet, it's alright. Kind of like the first time I looked at it, it's just a bunch of triangles. But we'll basically draw the z-axis here. We'll draw the z-axis here. We'll make this the x-axis. And then they all intersect at the origin. So this is going to be the y-axis. So this is positive x, positive y, and this is going to be z. It's kind of similar to this picture here, except we don't have the plane, so it might take a little bit for you to actually see the depth in it, because we're forcing the 3D onto a 2D piece of paper right here. So we're going to graph 3, -1, -2. So basically we're just going to go 3 steps in the x-axis, 1, 2, 3. We're going to go -1 on the y, and then we're going to go -2 right over here. So what does this point really define? Well, this point is actually going to be the vertex on a prism that has the side lengths of 3, -1, and -2. So to better visualize it, let's go ahead and draw that prism. So we have 1, 2, 3. We have -2, so we're going to draw, let's draw a dotted line right there. It'll be -1. And we have our little prism here. 1, 2, 3. And we're going to go -1. Alright, so this is going to be our little prism here, and then this point is going to be the vertex of one of the, where the edges intersect, right here. And the edge lengths are 3, -1, and -2. Now, if you kind of see the depth now, you see it's underneath the xy plane, so it's going to be either 5, 6, 7, or 8 for the octant. And it's also on kind of this side over here, where it borders the x and the -y. It's on this side, so that's going to be octant 8. So when we state the octant, it's going to be octant number 8. Okay, so that's basically just graphing. And then we have these two formulas right down here. And if you remember kind of distance and midpoint from 2D, this is very, very similar to those formulas. And it's basically the same thing. It's distance and midpoint, but for the 3D system. For 2D, distance would just be this component right here, without the z. But then for 3D, all we do is we add the z component here. So it would be x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and we take the square root of that whole thing. So this is going to be distance. And then finally, this one is going to be midpoint. So the midpoint would just be you add the two x components, you divide by 2 to get the x coordinate, you add the two y components, divide by 2 to get the y component, and then you finally add the two z components and divide by 2 to get the z value of that midpoint. This is going to be midpoint. Alright, let's take a look at this equation we have here. X minus h squared plus y minus k squared plus z minus j squared is equal to r squared. Now this is what we call the standard form of a sphere. So basically this is the standard form of a sphere. It looks very similar to the standard form of a circle. The standard form of a circle is basically this equation without the z component. But with the z component, it is the standard form of a sphere, and this depicts not the solid, but rather the shell of the sphere, the outer part, with the inside being hollow. Now, if you want the solid, then this would be an inequality. But since it's an equation, it's going to be basically the outer shell of the sphere. And this point hkj, which is x minus h squared, y minus k, z minus j, this hkj point is going to be the center of our sphere, and r, which is the square root of whatever this is equal to, is going to be the radius. Okay, so now we have this equation that's given to us, and what we want to do is we want to find the standard form of that sphere. And basically what we're going to do is we're going to just complete the square, so we can get this x minus h, this squared component on the outside. So if we look at these terms that we have here, they're all divisible by 9. And if we didn't know if 126 was divisible by 9, we just add up the digits. And 6 plus 2 plus 1 is 9. And since they add up to 9, it's divisible by 9. So if we divide everything by 9, we get x. Let me change the color. We end up getting x. Let's get color too. We get x squared plus y squared plus z squared minus 2x plus 4y plus 6z minus 14 is equal to 0. And basically what we do now is we just group the x terms, the y terms, and the z terms together, and we basically just complete the square. So we have x squared minus 2x, and 2 divided by 1 is equal to 1. If we square that, that's going to equal 1. And I'm going to underline it because I added an extra term here. Then plus y squared plus 4y, same thing, 4 divided by 2 squared is equal to 4. I'm going to underline that too. Plus z squared plus 6z plus 6 divided by 2 is 3. 3 squared is 9. Underline that is equal to, we'll move this 14 over, so we get 14 plus 1 plus 4 plus 9. If we simplify this whole thing now, we get x minus 1 squared plus y plus 2 squared plus z plus 3 squared is equal to 13, 14, 28. So that's going to be our standard form we have for this equation right here. And if we wanted to find specific things such as the center would be 1, negative 2, negative 3, or hkj. The radius would be the square root of 28, which is equal to 2 root 7 when we simplify. Okay. Now, we're given these 2 points, and these 2 points are the endpoints of the diameter. So let's put that here. That's a bad color. Endpoint of diameter. Okay, so we want to find the standard form equation. And what we need to find the standard form equation is we need the radius and we need the center. Well, we know this is the points of the diameter. So basically what we can do is we can find the midpoint of these 2 points, and that'll give us the center, and then the radius will be just the distance from the midpoint to any one of these points, and that will be the radius. So we're going to have 2 minus 1 over 2, negative 2 minus 4 over 2, negative 2 plus 4 over 2, and then 2 plus 6 over 2, and that'll just give us 1/2, 1, and then 8 over 2 is 4. So that's going to be our center, is 1/2, 1, 4. And now we need to find the radius, which is just going to be the distance from this point to either this one or this one. And I'm just going to pick the first one just because. You can also use the second one, you'll get the same thing. So the distance is going to be the square root of 2 minus 1/2 squared plus negative 2 minus 1 squared plus 2 minus 4 squared. So I use these 2 points. That's going to give us the square root of 61 over 4, which is going to be equal to, we can simplify it to root 61 over 2, but we only need r squared, so if you just square this whole thing, we get 61 over 4. So for the standard form equation, it's just going to be x minus 1/2 squared plus y minus 1 squared plus z minus 4 squared is equal to 61 over 4. And that's going to be our standard form equation for this particular problem.